I'd say I'm recording these lectures, and I am saving them, and I hope to get them posted and linked up onto Canvas so that you could go back and review them if you want to. All right, we said this is where we would get to, this symbol today, and here it is. I got these wrong. This is Z and that's A. I'm sorry. That's Z and that's A. And what is Z? Z is the atomic number, and A is the mass number. And what is X? X is the symbol of the element. So I'm using X as a general symbol now. We're going to replace X with one of these symbols off of the periodic table. And we're going to use that to describe these elements and distinguish them from one another. This is fairly simple. There isn't any real high math here. It's addition and subtraction. So it'd be pretty straightforward. I want to get this worksheet up here. So M2 is that worksheet. Look at that one right there. We'll go down to the bottom. All right, so here it is. So Z, the atomic number, that's the most important number here. So if you look at hydrogen, you see it's got a number 1 in that square. Helium has number 2. Lithium 3. Oxygen number 8. That is the atomic number of that element. And what is the atomic number? It's the number of protons in the nucleus of that element. And that is the most constant number you will see about every one of these elements. Any nucleus where there are only 8 protons in the nucleus is an oxygen atom. It's an oxygen nucleus. That is the most characteristic number of the element, number of protons it has. Z, A is the mass number. That's the number of protons and neutrons. So I don't think I've introduced you the concept of isotopes yet. Let's see if that's coming up on the next slide. I have my slides here. We need to kind of understand isotopes for a second here. So hydrogen is atomic number 1. That's its Z number. It's atomic number. That's the number of protons in the nucleus. And the most common hydrogen atom in the atmosphere, when you take hydrogen or make hydrogen out of water, just break water down into hydrogen and oxygen, the most common one you find has 1 proton and 0 neutrons. And A, the mass number, equals the number of protons plus the number of neutrons. On Tuesday I showed you that earlier slide, that had the mass of the proton, neutron, electron. Remember? And I said the protons and neutrons are almost 2,000 times heavier than the electrons. The protons and neutrons are just about the same mass. So if you want to know how heavy something is, you basically need to know how many protons and neutrons are in its nucleus. So the mass number for hydrogen is 1. And this is the most common hydrogen atom. Greater than 99% of all hydrogen, and it's like 99.9% of it, is this kind of an atom. However, there are isotopes of hydrogen. And what is an isotope? An isotope is atoms of the same element that contain different amounts of neutrons. All right? So there is a hydrogen form that has 1 proton and 1 neutron. Now, what would its atomic number be? 2. All right? We add those up. And that would be the symbol. This would be the symbol for that isotope. And that isotope is called deuterium. Deuterium. And it's heavier. And it's like approximately 0.1%, probably less than that, of a hydrogen. So if you had a cylinder full of hydrogen, you'd have a great deal of this isotope, a tiny little bit of this isotope, and a trace of this one. This one has 1 proton and it has 2 neutrons. So what is its atomic number? 3. And it is called tritium. Tritium. And you will see it just say trace. It's so little amount of it that it's 0.0000001% of it or something like that. It's trace. Very little bit of tritium. But tritium is heavier than hydrogen. It is heavier. That 2 of those together would be heavier. So we use these symbols primarily to identify what isotope are we talking about of that element. And different elements have different forms of their isotopes. Some of them have a whole bunch of isotopes. And what we're talking about naturally occurring in these particle accelerators and things like that, they have created isotopes that you don't actually find in nature. If you actually went out and dug up some iron ore, and separated it out into pure iron, you'd find different isotopes of iron. That's the naturally occurring isotopes. But if you took iron into a nuclear generator of some sort, you could make other isotopes of it. You could fire neutrons at it and make other isotopes. Okay? So these are isotopes. Isotopes are atoms of the same element that have differing numbers of neutrons. And this was, Dalton thought that every atom of oxygen would be exactly the same mass. He didn't know anything about neutrons. He didn't actually know about electrons and protons. So he really didn't know about neutrons, but he postulated that every atom of each element would have the exact same mass, and he was not entirely correct. Doesn't mean his theory is thrown out. It's modified a little bit. Hey, Dalton, we've discovered neutrons, and there are isotopes. And he would have applauded the advance of that information. So, let's see here. So we're into this symbol. Let's take a look. The atomic number of iodine. Okay, so I give you these periodic tables. I told you don't need to memorize this, but I want you to become familiar with it. It would be like if a friend of yours moved to San Antonio and you laid a map of San Antonio in front of them. Said, hey, let's talk. You want to go to the North Star Mall? Okay, don't go this way. Go that way. You want them to get familiar with the land and get comfortable with the layout of San Antonio. I want you to get comfortable with this periodic table. So I'll be always pointing over here and say, here's iodine. There's its atomic number. You can see where it is, down in the bottom left corner, 53. And then we have this number, 127, mass number. So how many protons are in that nucleus? 53. All right, now this number, the protons plus the neutrons equals 127. And if I take the protons, which is 53, and subtract it, I'm left with neutrons. 3 from 7 is 4, 5 from 12 is 7. Is that right? Check my math. I'm standing up. I think better when I'm sitting down and when I've had my second cup of coffee. So it has 74 neutrons. All right, so that number up there isn't telling you how many neutrons are in there. It's telling you how heavy this nucleus is, and what makes it heavy are protons and neutrons. Now electrons. Okay, one thing we left out, there is nothing here. Nothing there. Which means it has no charge. What does that mean? It means it has an equal number, that the number of protons equals the number of electrons. Okay, when there's no charge right there, every proton has been balanced out by an electron, the charge of the electron. So how many electrons does it have? 53. Okay. We will start, not soon here, but eventually we will start seeing some things up there. You'll see a plus or a minus, or a +2 or a -2 or a +3. You'll see some charges up there. Those are ions. I won't refer to them as atoms. It's the ionic form of that atom. It's gained or lost some electrons. But for right now, I'm talking about neutral atoms. So in neutral atoms, this is what's true. The positive charge has been balanced out by the negative charge. Okay, so that takes us right here. Find this worksheet and work that out for 2 or 3 or all of them. Protons, neutrons, and electrons. Just take a... Pardon me?
Which one? Sorry.
There you go. Find this on one of those worksheets, and I'll write these numbers up here in a minute, or call them out. You'll tell me what the numbers are. Just take 2 minutes. And if you get those done, then look at the top and just kind of see what you can do with some of those questions on that worksheet. And I hope this in-class stuff, and I explain a little bit, you do a little bit, I hope this helps solidify these things. Some of your, I haven't opened up the homework assignments for M2, have I? I haven't done that yet. Ooh.
You did.
For M2?
Yeah, you did. You just have it open the quizzes.
The homework assignments are open, but not quizzes.
Okay. Okay, and there's no date on, or there is a date on it? September 10th, I think.
Yes.
Yeah, the homework, okay, good, good. So you got some stuff to work on. I always want you to have stuff to work on. There's too much stuff to work on that keep you starving for the next assignment. I don't want you to be malnourished. Okay. If you didn't have time to do all these questions, let's just do this real quickly. Barium. Someone want me to give me the answers to barium? Protons, neutrons, electrons.
56.
All right. If anybody protests, just protest. Let me know. Next one. Someone else.
84.
No, someone else.
Proton.
What?
Number 2.
Number 2?
Proton.
Yep. Just go right across. How many?
Oh, sorry.
I'm sorry. I'm doing this one.
Protons 84, neutrons 125, electrons 84.
Okay. Chlorine. Someone else. Go ahead, KK.
17, 20, 17.
Okay. Fourth person. Yes, go ahead.
Protons 11, neutrons 12, electrons 11.
Okay. Krypton. Okay, Gene.
48.
All right, is everybody good with that? All right, it's pretty straightforward, but that's how we use that. KK?
For the neutrons, this last one, 48, I got 52.
6 from 14 is 8.
Oh, wait, I used the wrong number.
3 from 7 is 4. Okay?
What did you say, in the neutral what?
In the neutral atom,
Oh, okay.
protons equal electrons. Okay? And notice there's no charge. There's nothing here. This spot is blank. So that that spot is going to have, it's going to have, I can't write over there. It's going to have your atomic number. It's going to have your mass number, and then it's going to have charge. And if it is neutral, we leave it blank. In other words, we don't write a 0. We're not writing zeros in there. 0 charge. 0 is understood. If it is ever an ion, you have to put the charge. But these are neutral atoms in their elemental form, and that's how you find elements. So this aluminum right here hasn't combined with anything. It's not in a compound. So the atoms in that aluminum, in this aluminum bar right here, this aluminum piece, has the same number. It has all its electrons. It hasn't lost or gained any electrons. Copper, a copper penny is another element that copper pennies aren't copper anymore.
No, they're not.
They're made out of zinc and coated with copper.
Yes.
So, but I think, what was it, 1984 that changed? 1982? Early 80s. 82? I sat down with my grandkids doing this, and I can bring those pennies in here and weigh them on the scale, and you can tell that a 1981 penny is heavier than a 1982 penny. So you can tell the difference between the zinc and the copper by weighing them. But at any rate, in the 1970s, the pennies were copper. During World War II,
Steel, right?
they were made out of steel, because we needed the copper for bullet shells, and they stopped making pennies out of copper, started making them out of iron. So you had iron pennies. So in 1943, pennies rusted. Those of you, some of you might be coin collectors.
They actually have a thing with, there was a mistake, there's a mistake they made with a copper penny. There's a certain date, so they were supposed to transmit to steel. And so that date, I guess that penny's worth like $1 million or something like that.
Because it is copper, or it's...
Yeah, because it's a mistake.
Okay.
Yeah,
Okay.
something like that.
I do have a coin collection. I haven't kept up with it, but when I was a kid, I would collect coins. All right, let's move on. Molecular and ionic compounds, atomic and ionic. Here's a sodium atom. Sodium atom has a nucleus with 11 protons and 12 neutrons and 11 electrons. So we would be displaying this like this. That's your sodium atom. But what sodium atoms do, and actually everything in that first column right there behaves like sodium, they tend to lose one electron. Not many, one. Specifically one electron, and form an ion. And so if it's going to, so this has 11 protons, neutrons, electrons. It has 11 protons, 12 neutrons, 11 electrons. If it loses an electron, it's still going to have 11 protons in the nucleus. It's still going to have 12 neutrons in the nucleus, but now it has only 10 electrons. It lost an electron. And notice what happens to it. It gains a positive charge. So that is an ion. Not a neutral atom, it's an ion. And why has it got a positive charge? Well, take a look at this. 11 protons have a plus 11 charge. 10 electrons have a minus 10 charge. And if you sum those two things up, it results in a net plus 1 charge. And that's all we put up here is the net charge on this particle, which is now an ion, and it's positively charged. Okay, we'll talk a lot more about this, but so a lot of what we're doing right now is introducing vocabulary. What I will try when I talk about an atom to be talking about a neutral atom. And when it has gained or lost electrons, I will talk about it as an ion, and it will have a charge relative to what it gained or lost. Okay, so that's good enough for right now, the vocabulary. When this is kind of interesting here because this is an alpha particle. Remember Rutherford's experiment? They were firing alpha particles at gold foil. What is an alpha particle? An alpha particle is a helium nucleus stripped away of all of its electrons. That's what an alpha particle is. And if you took that, here is a helium atom. It has 2 protons, 2 neutrons, 2 electrons. Plus 2 minus 2 corresponds to 0 charge. But if you take a helium atom and strip away 2 protons, 2 neutrons, and no electrons, 0 electrons, plus 2 minus 0 is plus 2. And that is an alpha particle. It is, yeah, so that's an alpha particle. We won't say any more about that right now, but here's magnesium, where it has lost 2 electrons. And notice where magnesium is. It's in the second column. And that is its major tendency, lose 2 electrons. All right. And how did they discover this? Well, it wasn't into the 1930s, and I think this is Chadwick in the 1930s. And they've finally come up with a device now where they're kind of being able to atomize elements and fire them through a detector and a magnetic field. They'd ionize them a little bit, but they'd be firing a pure element. Let's say it's copper or iron or whatever, and they would start seeing it breaking up into a couple different beams. And so why these coppers don't all seem to be alike? And what they differed in was weight. And so because some were lighter than others, when they went through this field, they actually deflected further. The magnetic field had a bigger impact on them. They deflected further. The heavier ones deflected a little bit. So here's 1, 2, 3, 4, 5 different isotopes of the same element. And that's how they discovered the neutron. Oh, here it is, zirconium. So here's zirconium 90, zirconium 91, 92, 94, 96. And then they were also able to determine the relative abundance based on the intensity of these beams right here. They weren't all there in equal amounts. They were there in very different amounts. And so this is the most prevalent isotope. These two are about as prevalent, and then very little bit over here of zirconium 96. But these are the 1, 2, 3, 4, 5 naturally occurring isotopes of zirconium and their relative abundance. Okay, so we would say that the atomic mass of zirconium 90 is 90, and the atomic mass of zirconium 96 is 96. But what this then begs the question is, what is the average atomic mass? Okay, if we put this all together, how do we average all those numbers and come up with a number? Well, the number we're going to come up with, this is what we have on the periodic table, our average atomic masses. The average atomic mass for oxygen. On your periodic table, it's 16.00. Up here, it's 15.9994. If I round that number off, we haven't gotten to rounding numbers yet. But if I want to round that number off to just four significant figures, I have to say, what is that number? I'm going to get rid of this number, but that number is greater than 5, so I'm going to promote that number up. And that 9 is going to go to a 10. And that 9 is going to go to a 10. And that 5 is going to go to a 6. So I'm rounding that number off to 4 significant figures. That's what your periodic table has. Average atomic masses to 4 significant figures. So for example, on there, you've got 4 pieces of information. Wrong. 8. Okay? Atomic number, mass number. Oh, this is average atomic mass. Symbol, and actually the name of the element. Let's take a look at hydrogen. Hydrogen, atomic number 1. It's got the name. And What's your table have? 1.01? Yeah, 1.01. All right, so we're taking it out to do 2 decimal places. That one has 1.00795. And if I want to round that off to 2 decimal places, this is greater than 5, so that promotes up. Okay? I don't want you to get confused. This got a different number than that one. Those are just rounded off to 2 decimal places. These are a little bit more accurate. If you went to the National Bureau of Standards, they could carry some of these out to 12 decimal places. Just did really fine work, fine mathematics. So now what we need to learn before the period ends today is how do you calculate these numbers. So I will do an example, and then I've got 4 more there for you to do. Okay, there's the isotopes of hydrogen. We've gone through that. And there's a natural abundance of these, like 99.9%, 0.1%, and a trace amount. Here's a table. Let's look at the hydrogen. Here's hydrogen. No neutrons. 99.989% is the natural abundance of that isotope. This one, 0.0115%, and tritium is trace. So this has an atomic mass of, well, roughly 1, 2, 3, but they take these masses and the relative abundance to calculate this number. And we'll see how we do that. So here's helium, 2 isotopes, very, very little bit of this other isotope, almost 100% that one isotope. Lithium. So you can go into Google, you could go to Google here or OpenStax and look up all the elements, and you'll see different elements have different numbers of beryllium here. Looks like it doesn't have any isotopes, just beryllium with 5 neutrons. So it's beryllium 9. You could go walk right on down through there to oxygen. Okay, back here, boron. Here's boron. It has 2 isotopes. Now notice about 19.9% is this isotope, and 80.1% is this isotope. So now let's look at how do you calculate the average atomic mass for boron. All right, so what you do here, this problem is, out there is a word problem. So you kind of figure out, you got boron 10, it has an atomic mass of 10.129 atomic mass units, and there's 19.9% of that one. Boron 11.0093 atomic mass units, and it's 80.1. And I'm going to just promote these up to 4 significant figures. That's the relative abundance of these. And what we want to calculate, so here we're saying calculate the average atomic mass of boron. How do we do that? Well, take the percent and convert it into a decimal. What is 19.9% It's saying 19.99 per cent per 100. Out of 100 of them, 19.99 are that 10.19. So yeah, this is going to be 0.1990. So all we're doing is moving the decimal point over 2 places to convert it into a decimal. So I'm going to take the atomic mass times the relative amount. You're going to get a number. So I'm going to take 0.129 times 0.1990. And I'm going to take out your calculators because I'm going to ask you to help me do these calculations right now. 80.10 converts into what? As a decimal.
0.8010.
Okay. So someone give me this number.
2.0156.
And someone give me this number.
I got 8.8184493.
Is that right?
There's 1,493.
Two fours in there.
Yeah, and then
All right, we probably got a whole lot more numbers there when we need. What we're going to want to do is round off a number to 2 decimal places down here. So so now what you do is you add those numbers together. Add those 2 numbers together. And I don't know if I got this set up right. And you don't necessarily need to keep all those. What I would do, I think you could just do 2.02. I'm rounding this off, and 8.82. Let's see if that comes out all right for us. Do you see what I did? I just rounded this number off. I just rounded that number off. I'm going to get a 4, an 8, 10.84. It's coming out to 10.81. Let's do this here. 0. 13, 14, one up there. I don't know if I'm doing this right, but
it's 10.8. And then 4,103.
4103.
That's what we had.
So,
4,103.
is that right? Okay, so this is coming out to about 10.83, about 10.84. They're roughly the same, but that's the average atomic mass. Now somehow our periodic table there has got 10.81, and when you see any discrepancies, it's probably that the official number took into consideration some other isotopes that we didn't have on our list. Or they carried the atomic mass of those individual isotopes out a little bit further. Okay, so I think I would accept that number or that number as the average atomic mass of boron. So one thing, well, 2 things to keep in mind here. Number 1, this number is being derived from the various isotopes of the element that exist in nature. And it is weighted according to, in other words, you can see that this number is this number is closer to that number than it is to that number. Why? There are more of these. Okay? It is skewing the average atomic mass towards the more abundant isotope. Okay? And then number 2 is how to go through the calculation. So, go back to the other worksheet. I don't know if I got it up. I don't have it up here yet. But the other worksheet has doing some calculations. So let's do some of those. Let me see yours. All right, so you see this one here? What's it start out with? Chlorine. So take that data right there and work out the average atomic mass of chlorine. I'll pull it up here while you're getting to it. Worksheets, feel free to commiserate with your student next to you, check your answers, question one another, challenge one another. All right, this is a learning experience. The objective here is for you to get comfortable enough with this that when you see problems like this on a test or a quiz, you can solve them. How's everybody doing on that first one?
Oh, I'm right there.
Go on to others if you want to. Okay, let's look at chlorine. So the 75.78 is going to convert into that decimal. The 24.22 is going to just convert into 0.2422. And someone want to give me some numbers here? Let's see what you got, Ali. You've got 26.50. and 8.95. And then you should put units on here of atomic mass units. All right? Because these are atomic mass units. That's its average atomic mass. On average, a chlorine atom has a mass of 35. I'm sorry, 35.45 atomic mass units. On average. So you go to HEB and you buy a bottle of Clorox bleach. Clorox. The active ingredient in there is chlorine, but 75.78% of the chlorine in there is this isotope. It's this isotope. How did I get that? Well, this is roughly rounds off to 35, so that would be 35 protons and neutrons. How did I get that number? 17. Off the periodic table. If you're talking about chlorine, it's atomic number 17. There is no such thing as another element with atomic number 17. It's chlorine. It's like your fingerprint. There's no other fingerprint like your fingerprint. All right? That's chlorine's fingerprint, how many protons it has in its nucleus. All right? And so you multiply this out, add it up, and you get the average atomic mass. We won't do all of these, but this one down here is going to be times this number. And this one, 0.638%. We got to move that decimal point over 2 places. All right, you're going to multiply that one by 0.0068. There's not a whole lot of that isotope.
638?
638, thank you. .00638. And there's not a lot of this isotope in there, so this is just gonna tweak the atomic mass a little bit. And what element are we talking about? Nitrogen? Yeah, 14.01, something like that. Okay, I'll leave the other two for you to do. The answers I didn't give you there, but they should be posted in Newton. But let's see what else we gotta, let's see if we can, how many more slides are there? Okay, here's another problem. This is a meteorite. They're finding some neon in this meteorite. I can't believe that. That's a gas. What is the average mass of neon in the solar wind? Okay, they're talking about neon in the solar wind. And from it, figuring out what its average atomic mass is. That's just another problem. We talked about the electromagnetic spectrum the other day, and that covers the chapter. These last two slides are just showing that wavelength and energy are related. The longer the wavelength, the lower the energy. Radio waves have very long wavelengths. Radio waves, when you listen to the radio. It's electromagnetic radiation. It has very long wavelength, very low energy. X-rays have very short wavelengths and very high energy. That's what makes them injurious. That's what makes them harmful to us, is that there's such high energy. Okay, any questions? There's other questions on the worksheet. You can kind of just look at those. They're probably similar to some of the things you saw in the homeworks or the quizzes. And we've finished Module 2, so that means we're ready to go into Module 3, right? Which is compounds. I think that's, no, periodic table. Periodic table is Module 3. So we'll get that going, and what is today, the 6th? When is the 10th? Monday? And I think Monday the 10th, you have some homeworks due, and then maybe I'll get the quizzes due by the 11th, the evening of the 11th, on Module 2. All right? And then you can, and I'll get Module 3 homework assignments up there too. Great. All right, have a good weekend.